graphical methods for understanding the behavior of graphs, discussing limits, can fail us. We can run into some of these issues. So let's set up some definitions, some notation, so that we can start looking at discussing limits more accurately. So first, let's start off by defining what exactly a limit is. So before we introduce the definition, let's just go ahead and introduce the notation. So if we encounter a limit problem, it's going to look like this. So we're going to start with this notation LIM, so the limit. Underneath that, we're going to see x with an arrow to a c. So that means the same thing as what I said before. X is approaching c. That's going to be listed in front of some function, f of x, g of x, whatever function we're dealing with. And that limit is going to be equal to some value L. So when we see that notation, to read it, what we're saying is the limit as x approaches some value c of f of x is L. So what we're going to be interested in finding is that value for L. We're going to be given this problem on the left-hand side, some function, a value that x is approaching. We want to determine what is the limit of that function. So to define what a limit is, we can say that if f of x gets closer and closer to some value, so if our function is getting closer and closer and closer to some value L, whatever that value happens to be, as x gets closer and closer and closer to some value c, then the limit as x approaches c of f of x equals L. So when I used the word around previously, what I meant by that was this idea of getting closer and closer and closer. We don't ever actually have to get to the point where x is equal to c. We're just getting closer and closer to that value. So as we get closer to that point, what's happening to our function value? So we can talk about limits. We can also consider what are called one-sided limits. So one-sided limits also relate back to what I was talking about before. A one-sided limit is as we're approaching some value for x from just the right-hand side or from the left-hand side. So we can look at the limit as x approaches c from the right-hand side. To indicate that, we put a little plus sign, almost like we would write an exponent for the c. So if we see the limit as x approaches c to the plus, we mean we're approaching that value of c from the right-hand side. So the limit as x approaches c from the right-hand side of f of x equals some value k. And let's again just write this in. So as x approaches c from the right, and we can talk about as we approach c from the left, which we designate with a c and then a negative symbol. So again, kind of written like it was an exponent up there, but what we're just indicating by that is that whatever that value for c is, we're approaching it from the left. F of x equals L. So again, what we're saying here is that as x approaches c from the left, so that negative symbol, the positive symbol, they don't mean that the value that x is approaching has to be a positive or negative value. They just tell us about the direction we're approaching from. So keep in mind, a negative up here isn't the same thing as a negative in front of that number. So just talking about the direction we're approaching from. And the reason we want to consider these one-sided limits is a very powerful theorem that's going to help us solve a number of different problems. The limit as x approaches c of f of x is going to be equal to L. And then we've got this double arrow, which means if and only if. So meaning this equality goes both directions, that the left-hand side is true, the right-hand side is true, and vice versa. So if the limit as x approaches c of our function is L, then the limit as x approaches c from the right-hand side has to be equal to the limit as x approaches c from the left-hand side. Both of those one-sided limits have to be equal to L. So one way for answering this question, what's the limit of our function around some given point, is to look at the left-hand limit and right-hand limit. If those are equal, then we have found the limit for our function. So let's take this notation, and we want to apply this to the graph that we already talked about. So again, we're still interested in what's happening around each of these x values, but now we've given that a little more definition, a little more context. We're talking about what's happening as we get closer and closer and closer to some specific value. So for x equals negative 1, we're still interested in as we approach from the left and right-hand sides. So we can start off by considering as we approach from the right-hand side, x is approaching negative 1. And then we put that little plus symbol to indicate approaching from the right-hand side of f of x. In this case, as we approach from the right-hand side, again, we're getting closer and closer to that value of 4. So our right-hand limit of our function as x gets closer to negative 1 is 4. We can consider the left-hand limit. So in this case, we're looking at it as x gets closer to negative 1, and then that other negative symbol to, again, just indicate the direction that we're approaching from of f of x is, again, as we trace along this graph, we're approaching 4. So in this case, our right-hand limit, left-hand limit are both equal to 4. And by that theorem that we just introduced, that tells us that the limit as x approaches 1 of our function is equal to 4. So in this case, again, we looked at the left-hand limit, right-hand limit, and that gave us this final answer for the limit of the function at that point. So as x gets closer to 1, our function is getting closer to a value of 4. So let's look at our next example, as x approaches negative 4. So we'll start off the same way. We'll consider the limit as x approaches negative 4 from the right. So again, this is where we saw that our function is approaching two different values depending on which direction that we're heading from. So as we approach from the right, we're approaching a function value of negative 2. As we approach from the left, again, by tracing along our graph, we see that we're approaching the function value of 3. So in this case, the right-hand limit, left-hand limit are not equal to each other. So we would say that the limit as x approaches negative 4 of f of x does not exist, or for shorthand, DNE. So just to save me from having to write that out over and over again. Since the right and left-hand limits are different from each other, the limit as x approaches negative 4 doesn't exist. And again, that comes from that theorem that we just introduced up above. So as x approaches 2, and again, we'll consider this from the left and right-hand sides. Again, we're going to see that this is approaching two different values. From the right-hand side, we already talked about how that's getting closer and closer to a function value of 5. The limit as x approaches 2 from the left-hand side is approaching a different value, in this case negative 1. So again, since the two one-sided limits are not equal to each other, we would say that the limit as x approaches 2 of f of x does not exist. There is no limit at that point because from either direction we come up approaching different values. So in our last example, again, we already took a look at this. We are approaching x equals 4 from both directions. We're arriving at that same value, again, even though our function is undefined. We just have to look at it as we get closer and closer and closer to that point, but not actually equal to it. So the limit as x approaches 4 from the right-hand side equals 2. The limit as x approaches 4 from the left-hand side equals 2, which means the limit as x approaches 2 of f of x is equal to 2. And again, keep in mind that that limit exists despite the fact that f of 4 is undefined because of that open circle. So it's possible in our first example, we had the function was actually defined at 4 and the limit is 4, but here our function is undefined at 4, but the limit still exists. So we can have either case happen. The function doesn't have to be defined in order for the limit to exist. All we need are those right and left-hand limits to match up. So at this point, all we've talked about is this graphical approach. Now we've introduced some notation, but again, we're still looking at a graph, using that graph that's up above to come up with these different limits. Since that can be misleading, now that we have this notation, these different theorems, we want to introduce some properties, some additional theorems that are now going to let us solve these algebraically without having to look at graphs.